Yeah, we can start. So our so even kind of a small school days today, but still welcome our friend Mehdi, who will tell us something about graphs and induced and stuff.
Right. Thank you. And well, thank you for inviting me here. Yeah, so today I will talk about it's a particular subject in the context of loop quantum gravity. I try to make it rather less technical than it could be, and I hope you are very welcome to ask questions to me at any point, and yeah, and I hope that you will manage to take something out of it. So subject of my talk is the graph coherent states in loop quantum gravity, and it's basically about the construction of new coherent states in this context. And roughly speaking, those coherent states are well, unlike what we are used to usually, they are adapted to some sort of graph excitations in this context. So I'll start with an introduction. So it will be a brief introduction to roughly loop quantum gravity and the problematic that I'm trying to solve here. And then I will move on to the construction, and I will give a couple of examples in simple cases how this construction can be carried on, and conclude with some comments and outlooks. So loop quantum gravity. So what it is? Loop quantum gravity is an approach to define a theory of quantum gravity plus matter, in a sense. So it's not really a theory of unification. However, nevertheless, if one is to define a theory of quantum gravity, one has to always think about including matter, and this is simply a consequence of Einstein equation. One side you have geometry, on the other you have matter field, and therefore both of them have to be quantum, and whatever quantum gravity theory you can come up with, you have to have somehow a way to incorporate the matter fields. Central, let's say, core principle of this approach is the background independence, which means that it doesn't assume any background metric whatsoever. It's quite it's generic in a sense, and the diffeomorphism symmetry is also taken very seriously in the theory. As for the quantization strategy, it is built on what we call quantization of the holonomy flux algebra. So it's a lot of fancy words, but basically one starts from, let's say, from GR that you could formulate as a gauge theory. So think as a gauge theory like in Yang-Mills theory. You can do the same with GR, where you have a connection and a conjugate momenta. And the next step is to do a quantization which is actually background independent. You do not consider basically the standard variables that are the connection and the, let's say, if you want in Maxwell theory, it would be the electric field or the conjugate momentum, because they are too singular. So we need to proceed with some smearing. And in that case, well, the connection naturally actually gets smeared in one dimension and exponentiated with some order whatsoever, but those are just technicalities that I would skip, but that's what gives the holonomy. And in a way, the dual smearing will be, in this case, the smearing for the fluxes. And naturally, because of the Poisson structure that you have from the connection and the conjugate variable, you obtain some algebra, which is what we call the holonomy flux algebra. And then you quantize that actually very similarly to what you would do for a quantum mechanical system, basically, after some complications. But at the end of the day, one obtains a Hilbert space or spaces depending on some, let's say, nuances that you can consider of quantum geometry states. The gauge symmetry at the end of the day in the theory, so in 4D, if we take the theory in 4D, what we get is that we have a gauge symmetry group, which is, we have SU2. This is pretty much the gravity sector. This is what is the internal gauge group that remains in the connection that we consider. there is G here that I put, and this G stands for all the symmetry groups for matter fields. So for instance, if you couple the Young mills or you introduce other matter fields, you can include the gauge symmetry group there. And finally, the one that persists from general relativity, which is the diffeomorphism group. Now, once you obtain your Hilbert space, in principle, the idea is to implement those gauge symmetries. In other words, you need to gauge out the degrees of freedom and the non-physical degrees of freedom. And there are, well, various approaches to do that, but not, you never get actually to the final, say, physical Hilbert space. But that I would say it's rather expected already. But the way you can proceed is, for instance, you consider that gauge symmetries are imposed by constraints. Those constraints are then imposed on your quantum states, and you can introduce some operators. And in fact, let's say the algebra of operators that you can introduce is quite large. There are in particular those which are interesting that are what we call geometric operators, and those are corresponding to some geometric quantities that, let's say, have some classical interpretation in the classical theory. And there I mentioned, for instance, the area, the volume, the curvature, and so on and so forth. However, at the end of the day, those gauge symmetries translate in some constraints. And the question is how to implement them. And there, as I was saying, there are various approaches. There is a more of a constraint approach, which means that you would define an operator corresponding to this constraint and try to solve it in the quantum theory. And that works to some extent. And for some other symmetries, that may not work well. And then one has to come up with other ideas. And then there is the methods of group averaging and so on. And there is one thing that would be left in a sense, which is the quantum dynamics. And in this case, the quantum dynamics is there are various angles one can look at. One is what the canonical formulation, which is basically what Hamiltonian formulation. So we try to get the Hamiltonian constraint from the classical Hamiltonian formulation of GR. And then we end up again, we follow the spirit of Dirac quantization, and we say that let's try to impose that. Now, that's very difficult in the sense that it's very difficult to solve this constraint in the Hilbert space, like finding the full set of solutions, so on and so forth. But on the other hand, intuitively, it's understandable because it would be equivalent to saying that one is able to find all the solutions of Einstein equations. And we know that's not doable, it hasn't been done, and therefore expecting to do so in the quantum theory might be too ambitious. And another approach is to consider the path integrals, and there you use some covariant formulation and you introduce some discretizations. Discretizations usually breaks symmetries, but then you have to, you try to get rid of them. You consider them, or you think of them as some sort of regulator in the theory, and you try to get rid of them at the end of the day. And there the approach is entirely different, but I will not dwell on that too much. So at the end of the day, what is missing in this approach, in a way, what is missing is actually a semi-classical and continuum limit, which what we mean by that is a regime of classical and continuous space-time. Identifying a full regime, such a regime, actually is still somewhat a work in progress. There are various approaches to it. Nevertheless, the issue is quite open. Another point is the implementation of space-time symmetries, meaning that, for instance, if you go back again to the classical theory, you think how you would approach solutions to Einstein equation, you would try to implement some sort of symmetries. Symmetries will simplify the equations, and then you get to some sort of solutions to Einstein equations with some particular symmetries. We have you consider some Killing vector fields and so on. When you have a quantum theory, this is much more difficult to understand, since you lack this say smooth geometry. Then imposing symmetry is well, it's more problematic, and one has to think of more novel ideas to do so. Some of those ideas, for instance, are approaches such as coherent states. So the construction of coherent states, basically, like you would do in some quantum mechanics, is basically you would consider some states which would manifest some coherence and semi-classical properties with respect to certain set of observables that you would be interested in. Another approach in this context of the semi-classical and continuum limit is a whole business usually named renormalization. But renormalization here is really to be understood as somewhat trying to understand how, and you would see a bit of that later, how to get from a set of finite degrees of freedom to a set of infinite degrees of freedom. And that's how we would imagine somehow states which would encode a continuous spacetime to be. In the context of imposing spacetime symmetries, there is also the idea of trying to impose some sort of constraints. So you can, for instance, in the case of homogeneous isotropic, you try to derive some classical constraints that you impose such symmetry. Then you try to quantize them and associate an operator for it in the quantum theory. But sometimes it turns out that this is actually too much. It is too much because in the sense that, well, again, this is something that manifests in quantum mechanics. If you take a huge set of observables and expect that, and you quantize them, you cannot expect really that all the commutators will somehow will not display any anomalies with respect to the classical Poisson brackets corresponding to those observables. And that's usually what happens here. Because one has to remember that I refer a lot to quantum mechanical systems because there are a lot of similarities. Nevertheless, here it is actually a field theory. It is a field theory which is cast into some sort of uncountable sum of finite degrees of freedom, subsystem with finite degrees of freedom. And this is what I would see in a moment. And those are graphs. But the general idea, there is a common thread here, usually among all this, is the notion of coherent states, which dictates naturally some sort of choice of observables. So you are interested in some observables, and then you try to construct some states which behave nicely with respect to them. So as I was saying, in this context, in loop quantum gravity, one can construct a Hilbert space of quantum geometry. This Hilbert space actually is not one, but it could be a few of them, depending on what would you like to consider. So for instance, there I gave you 3 examples. So the kinematical one is basically this Hilbert space that you would get simply by quantizing the holonomy flux algebra and doing nothing else. The next one, for instance, in which you try to impose some sort of partial diffeomorphism symmetry, and we'll come back to that. And the last one is when you try to impose a full diffeomorphism symmetry in your Hilbert space. But they are entirely different, as for instance, those 2 Hilbert spaces at the end, they lie in the dual space of, of a dense subset of the kinematical one. Anyway, so you can introduce in those Hilbert spaces, you can introduce a basis. So you have basis states, and those are usually what you call, in the context of gravity, spin networks. Why do we call them spin networks? Because as it turns out, remember, I told you that the gauge group of gravity sector here is SU2. So when you quantize SU2, it's basically a rotation. So what you get is spins. You have spin representations. The graph, where it does come from, it comes basically from what I was telling you about holonomies. Holonomies are basically manifest, they are they come from a smearing of the connection along one dimension elements when we are working in 3D. And this is what gives those lines. If you have a collection of them, you get a graph. That's what we get. The last element may be, sure.
This is kind of a very good question. How do you generate this construction? I mean, at the end, what really wants to start is actually to find a Hilbert space on which these groups, the symmetry groups are represented.
That's correct.
Yeah. Now you choose this particular Hilbert space because it actually solves for you for free the gauge constraint.
right?
Some of the gauge consider, yeah.
So, I mean, the gauge SU2.
Yeah,
It's
yes.
automatically because of the Wilson lines, you know. Right.
Uh,
So
well-
there are gauge environment objects, right? So you build the space of gauge or SU2 gauge environment objects.
You can, if you do it, you can do it going
But
through
now
the
the
Wilson loops.
is
Yeah,
fine, that's fine. And then you want to represent, you know, the Formosa.
that's correct.
Now the question is to what extent this is the generic solution of the problem, or is it a very special solution?
So here I didn't talk a lot about I didn't mention yet the diff symmetry and how we solve it in the quantum theory, but definitely it's not, there is no unique approach to do so. And the reason for that is that if you look at the diffeomorphism action, let's say, and you think about the generator, you'll find that actually it's not well defined on, for instance, that space, which is the kinematical Hilbert space. It doesn't have a well-defined action. So what usually people do is, well, there are several approaches. The most radical one, if you want to stick to Dirac's quantization spirit, is to say, still, I have to impose it as a constraint and solve it exactly. Then what you find is actually the action of those diffeomorphisms actually.
This was not my question.
So
My question was, why you actually start your construction in kinematical Hilbert space. Instead, you might think, for example, of solving the homomorphism first, and then imposing SU2. Right? Because the idea here is to get for free the solution of SU2, and then try to work it out, and it leads to all the problems that we know about. Now the question is, in this construction, just a particular construction,
it is a
or is it possible to find some different construction?
It is a particular one, but there is no other one. The reason for that is basically you do not know how to solve diffeomorphism.
No other one.
Yeah.
Okay.
In other words, if you want to approach it from this spirit that you want to quantize some sort of algebra, classical algebra that you have, and you take that the diffeomorphisms are actually, let's say, that this gauge symmetry somehow is fundamental, and it has to be imposed strictly. So either you solve it fully classically, and then you reduce, let's say, your space of solutions to the physical one, and then you quantize that, or you quantize first this normal phase space, and then you try to impose it in the quantum theory. The problem is that we cannot do the first one, which is when we reduce the phase space with respect to diffeomorphism. So that we don't know how to do, like generally on the full phase space of general relativity. And because we cannot do that, then we do the other way. And of course, the catch is, once you do that, yes, you can go to a quantum theory, you can define a quantum theory, but then you have difficulties in imposing the diff symmetry. So in this, there are ways of imposing the diff symmetry by, instead of thinking about it as an action of the generators of the group, you take actually finite diffeomorphism and you try to average over them. And this what gives you actually those two other Hilbert spaces there that I mentioned. There are other approaches which state, for instance, they are more radical and they depart a bit from this Dirac quantization perspective, which is to say, actually, the diff symmetry should only be emergent in some regime, and it should not be somehow strongly imposed in a quantum theory. But that leads to different approaches. Actually, for instance, spin film is one of those approaches which consider that diffeomorphism symmetry should be recovered in some regime, rather to think about it as somehow fundamental. All right, so as I was saying, at the end of the day, the basis states that we end up with take, like, if you want to represent them graphically, you have this graph composed of those holonomies. You have those representations of SU2 because it's the gauge group, so each representation is associated to an edge, which means that this is the representation of this holonomy as a group element, okay? And then you have this, what I call iota there, which is basically what we call intertwiners, but this is, you see in usually non-abelian gauge groups. So when you couple multiple representations, right? You have a tensor that couples those different representations, like what you do in spin systems, basically. The only particularity here is that because we have this SU2 as a gauge group, so we need to impose some sort of gauge invariance. And then that you can do, it's easily done. And then what you obtain basically are those gauge invariant tensors, which couple those various representations. And basically those states form a basis, and basically the Hilbert space would decompose as some sort of direct sum over graphs. Here I call them graphs, but depending on which Hilbert space you work, it's actually a class of equivalence. And you have the spins that label, and then the intertwiners are there. So remember that since you have a like finite set of spins on each graph that meet, then the space associated to this intertwiner space is always finite dimensional. And yes, so that's about that. So a spin network will be usually labeled by those three labels. So you have an oriented graph, a set of spins associated to the edges of this graph, and a set of intertwiners associated to the vertices of this graph. All right. Then you have this set of operators, which basically comes from your quantization. So you have the holonomies and fluxes, which those would have a natural action in your Hilbert space. Then you can construct some area operator, which basically is quadratic in the fluxes, the volume, the curvature as well. So here I talk about the scalar curvature, but you can also construct some operator for the extrinsic curvature. And more importantly, for instance, is the Hamiltonian operator. And the Hamiltonian operator here is basically the operator for the dynamics in the canonical formulation. So you have to define a Hamiltonian operator, and so on and so forth. And there we could go basically to, so we have this Hilbert space. We have this, we found some nice basis that we can describe nicely. And now we want to get somewhere with it. So we want to consider some observables, and then we want to get some sort of semi-classical limits, some interpretation of some state or some states which carry an interpretation of some sort of semi-classical space-time, as we are used to in the classical theory. And then there are various approaches. And here I'll try to categorize them in some sort of boxes with respect to the, let's say, quantum numbers that we have in the theory. So for instance, if you think about the intertwiners, then it is possible actually to construct some nice coherent states, okay, for each, basically for each vertex. So you have some intertwiner space, and then you can construct coherent states there. They are coherent with respect to those operators that basically act only in the intertwiner space. In this way, basically, that when you take, for instance, a spin network state, as I was saying, labeled by graph, collection of spins, a collection of intertwiners, the resulting state is simply a state which has the same graph, the same representations, just a different set of intertwiners. And if you have such operators, then you are able to construct some coherent states. And there is an example there, which is the Levin-Speziale coherent intertwiners. And they have a nice interpretation, semi-classical interpretation, in the sense that basically those coherent states represent some sort of polyhedra around, embedded in 3D, around each of the vertices. Then there is the another point of focus, which is if you consider a set of operators, which basically maps your spin network states in such a way that it changes only the spins and the intertwiners. And there is a very nice construction introduced by Thomas Seaman, where basically he uses this notion of complexifier. But basically, give you here an example, is basically you construct a coherent state for each edge of your graph, or if you want each edge of your state. And it's basically here, the simplest example is to have just a Gaussian over the spin that is there. Yes, and then the question that was always open, and I'll come back to that because it's actually important in the context how you define, for instance, certain observables. In the algebra of observables that we obtain, there are those observables which actually change graphs. In other words, they'll take a spin network state and maybe they map it to another spin network state where all the quantum numbers are different. And this graph excitation here that I denote in blue can be varied depending on what choice of, let's say, of how you define this operator, or what the graph excitation you want to introduce and so on. And the open question was always, can we construct some coherent states for this? And it's relevant because such operators which do this mapping, one of them, for instance, that was proposed is actually the Hamiltonian operator. So that's basically the motivation for why this actually could be interesting and it's worth looking at. All right, any questions at this stage? Before I, next section, I will go with the construction of these states. So if you have any questions before. All right. Very well. So here I will present briefly what is the concept of the construction. So a generic graph change. So if you have some initial graph, then you implement some graph change. Either you add an edge, or you add a closed loop, or you put in a vertex somewhere connected to the others. With a finite structure, namely that if you start with a finite graph, the number of excitations that you can create is always finite. Then this actually, such action provides a decomposition of the Hilbert space that you have into separable subspaces. And these separable subspaces, naturally by construction, will be stable under the action of such operators. Now, this here, this decomposition would be labeled by some graph, which actually, or by set of graphs, which actually have no excitations whatsoever. Any of such excitations that such operators would do. Very well. Then once you have this decomposition, then the question is, you look at the Hilbert space associated to this graph, and then you start putting excitations. Start putting 1, 2, 3, and you go on to infinity. You will generate some sort of this Hilbert space right here. And now the question is, can you somehow put some structure, restructure? Something happened. Back. All right. So the question is, or let's say the idea behind it, is to take this Hilbert space here and to try to put some structure or some reorganization to mimic precisely some sort of a Fock-like structure. So you reorganize this space such that it has this similar structure to a Fock space, or if you want, even to a structure just of the Hilbert space of a harmonic oscillator. Here I wrote that this S, that this Hilbert space by itself can be decomposed to this like sites, if you want, in the graph. But namely, what I mean by that is basically that whenever you take a graph excitation, whatever it is, because it has a finite structure, it will have only an impact on some finite subset of your graph. And this is what I would call a site. So you could be as well the whole graph at once, but that's still a subset. So what you can do is just you split your graph into those small sites. And the question is this space that you end up with somehow can be reorganized in this nice way? So how would we proceed generically? So take a graph change that basically, as I told you, has to be finite on some graph, which is colored. And here colored means just simply that it has spins and intertwiners where it should. And here, let's take for example, this simple example, which is of this closed loop. So give me any graph. I go at the vertex and I will tell you my graph excitation will be just a closed loop. I add a closed loop at the vertex. Then the idea is that construct the structure of a harmonic oscillator, which is basically you take every time you add an excitation or a loop, you consider that this is your somehow number state excitation. All right. So here, to give you, to simplify even things more, I will think only about a graph or a vertex which have just those two edges. And that's what I usually call a wedge. But basically a wedge, and then your operator that you start with keeps adding those closed loops on and on and on with the multiple action of this operator. And yes, and then I'm telling you, okay, fair enough. Structure your space such that any n number of excitations in your site correspond to some number state. And that's basically the generic idea, in the sense that once you have this number states, you basically, what you did is that actually you reorganized your Hilbert space in this way that it mirrors the Hilbert space of a harmonic oscillator. Then the question is just to figure out how those operators that you start with in principle that know nothing, it's not true, because we just reorganize, is whether you can extract from that the full canonical structure, namely annihilation and creation operators. Because then once you have this canonical structure, the idea is basically once you have your annihilation and creation operators, you consider just this canonical coherent states, which are, in other words, those states which are eigenvectors of your annihilation operators. So I'll try to exemplify this in a simpler case, which I will consider the case of a U1 gauge theory. So here I even simplify, it's not gravity per se, but this is like, think of it as I'm going to a Youngman sector, so Maxwell sector. So I have U1 gauge theory, and I will take the graph excitations to be just those closed loop that I just showed you, and let's see whether we can perform this construction more precisely. So
a question.
Sure.
Yes. So maybe this is what you are going to now explain precisely. But of course, if we have the space of states numbered by integer, then we know how to introduce the creation and annihilation operator just by introducing some coefficients and by saying that this creation operator adds maps n to n+1 with suitable coefficient.
Yes.
Now the problem in our case is that there are more degrees of freedom. So
that's correct.
So even in the U1 case, there are some degrees of freedom in the way this loop is connected with the other loops in the vertex. So my understanding is that you solved all those problems and that your definition works, include even taking into account all the other degrees of freedom.
Well, when I say define, for instance, a graph change or a graph excitation, then of course it has to be defined specifically, in the sense that, for instance, if you add a closed loop, then you have a precise prescription to add this closed loop in such a way that there are no ambiguities. All right. Then, of course, which I will come back to later, when you have, for instance, a non-abelian gauge group, which is the case in gravity, you have additional degrees of freedom, those intertwiners, for instance, and other stuff. But actually, even here with the spins, here I consider this small closed loops because it allows me to not touch actually the spins. I modify the graph. I will modify the intertwiners later on when I have a non-abelian gauge group, but I do not touch the spins of the graph. But in principle, it's not difficult either, because you have, when you change the spins, you just do some sort of recoupling of the quantum numbers. And this is also some sort of, let's say, discrete structure that you have there. So in principle, you can also map it. But perhaps it will be clearer when I go to the non-abelian case, and I'll show you how we deal with the intertwiners, for instance. The fact that you have a space of intertwiners, so it's some sort of degeneracy in there. So yeah.
But even in the U1 case, there seems to be more inequivalent ways of adding.
Of course.
Adding a loop. You may just add a closed loop, which is just closed by itself, or this loop can be cut and connected with some other the part.
Absolutely. Absolutely, you can. And in this case, they will be two different graph changes. And you have to just, the most important thing is to, whenever you give me a graph, just it is well defined. It has its own prescription. There is no ambiguity in defining it. Just give me a specific prescription that fixes it. And then I can construct because remember that this graph change is not just hypothetical, but what I'm interested in is some operator, some observable that I have. So this observable has to be well defined to begin with. Once it is well defined and its action is well defined, then there is no ambiguity anymore. You are giving me already an action which is well defined. So, and that's all I need. Basically.
Yeah, but this is not about not only about non-ambiguity, but also we want A and A dagger to have a proper commutation relation. They have to.
That's correct. Yes.
Exactly
Yes. You do need to have the proper commutation, and I will mention an example. Well, it's not always. Well, I'll mention an example of that where it's actually not possible. Well, once you consider some observable, you will not be able to find exactly, well, you have to think it carefully, but I will show an example and perhaps we can go back and tell me what you think. Okay. So yes, U1 gauge theory. So in the U1 gauge theory, so we have basically, what, U1 representations. I chose to label them by integers. The holonomies are basically, as I told you, they are defined by the smearing of the connection A and then the exponential. Here I take K just to be a positive number, but that's because this property of the holonomies, I can flip the sign and that's basically just the inverse. So there is no need to do it twice. I consider just the holonomy and its inverse. And then you have the fluxes. So those are basically that come from the electric field. So the smearing of the electric field along some two-dimensional surface S that intersect this edge E. And this is basically the action. So the action is what you get, just this eigenvalue, which correspond to the basically the representation. The basis states here will be simply labeled by graphs and the spin, those colored networks. Before we call them spin networks because I was talking about the C2 and spins. Here it's going to be just gamma and K because the coupling in U1, recoupling in U1 is simply trivial. So there are no intertwiners. So you just need the graph and the corresponding representations. All right. Then I will take, as I mentioned to you, a graph excitation which consists just of these closed loops, which there is a prescription of how to attach this loop so that it's not ambiguous. Moreover, it has to this operator, for instance, that you can consider that creates such loop. And whenever it acts multiple times, it will create as many loops. The property that you need, for instance, about those loops is to have some sort of bosonic statistics, in the sense that if you want let's say, in a way, in the context of graphs and of the theory, those loops will be indistinguishable. So that's what it boils down to, and that's basically it. So basically, this is my operator to start with that gives me my graph change. This operator, whenever I act multiple times, it will keep creating more loops, and then I have, because of this simple graph change that I chose here to exemplify the construction, the spins are not touched. Well, the colors here are not touched, so those representations are not touched. I don't have any intertwiners, so nothing is changed. So basically, the only structure that is changed is the graph by those additional loops. Then the one can simply introduce the canonical structure by saying that basically, if I, as I was mentioning here, if you define this as being the number states, then the one state with zero graph excitation, that will be your vacuum. The state, the number states, namely you would define this annihilation operator such that it acts on this number state and it gives you the one below. So it removes one excitation with some factor. And the creation operator would give you, will move you up with a specific factor. And of course, because there is no additional structure here except of the graph, excitation. This is basically just a harmonic oscillator space. And you have your commutation relation that are satisfied and so on, which you can write explicitly. Now, what is the operator correspondence? Then you go back basically to this operator that we are interested in that generated this graph change, this trace of the holonomy. And then you ask, what is the correspondence? Then if you define your canonical structure as above, then what you get is this. Basically, that what you need is the difference, for instance, between this operator and the creation operator is just this additional factor that pops up in front. So what you need to do is simply to remove it. And to remove it is you introduce this operator nu, which is again just given by your canonical structure operators. So this is basically the relation. And for the fluxes, well, for the fluxes, if you think about the flux of one edge, then you don't get much there, because here the operator started with depends only on holonomies. So the fluxes wouldn't care. It will remain just this diagonal operator with the eigenvalue given by the colors, the representations. However, if you consider something a bit more complicated, which is an operator that depends on the fluxes, all right? But in this way, that you have this abstract sum over all the possible loops that you can have in your states. Okay.
But can I ask what do you mean exactly by this V operator? In your previous example, it seemed to be just the number coefficient.
It's number plus one.
Well,
right?
Yeah, I mean it's just some factor, some number.
It's just some factor.
Yeah, and I see, and it commutes with A in particular.
Will it commute?
Just to make sure.
No, it wouldn't commute with A. Why would it commute?
Well, because it's just a number.
Well, not quite.
Okay, so what is it?
Well, here, I wrote it here in terms of the annihilation creation operator. So the last part. It's this inverse square root of this operator AA dagger. So when you compute the commutator, it won't be just zero. No.
Okay, but in this example, which was at the previous transparency, this operator was just multiplying by a closed loop.
That's correct.
Right? No disconnecting. Just we multiply by a closed loop.
Yeah.
So what is a dagger? A dagger is just.
So I give you here the expression in terms of the number operators. So take for instance a state n. Okay. If you hit it, so this is the operator that I was considering at the beginning. So this trace, right? This trace is defined as this A dagger nu. Okay. Now,
are you doing something?
Well, I'm just showing, but I'm not sure you can see. Can you?
No.
So I'm just talking about here this expression. So this correspondence here.
Which one?
Here, well, in the loop holonomies. So the correspondence. I don't know if you see. You see the Zoom video? Or maybe not.
No, I'm sorry. I'm.
Okay. Can you see the mouse now?
I see. Yeah. Now I see them.
Okay. So you have this trace operator here. That's the operator I started with, and I'm telling you that it's actually equal to this A dagger times nu, where nu is given by the line below. So say you take a number state. Okay. You take a number state and you hit it by this operator nu. So this number state, this operator nu will produce just a number. Namely, it will be number of excitations plus one, okay? And then the square root inverse, okay? And then you hit by the creation operators. And the creation operator will move you up, okay? As it is shown here on the line above. And it will produce...
Okay. I think I understand. So you mean that this V operator is a number, but this number depends on state. So
exactly.
That's why.
Yes. So number depends on the state, and that's why.
Okay. 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 Thank you.
It basically, if you want, is the operator here in this case that normalizes the A dagger.
Yeah, yeah.
It
Okay,
normalizes the A dagger so that you get the trace. But it does not commute, so the ordering is important. When I write it as A dagger new, it's A dagger new. And it gets flipped when I'm thinking about the annihilation operator, which is the which is the dual operator for that trace. Yeah. Okay. So I was mentioning the fluxes, and I was saying that in the case of the fluxes, you can go generally and consider some abstract sum over all the loops that exist in your state. And there you will get that actually the correspondence would be given by the number operator. And here, just to tell you, in principle, one cannot see the relevance of this, but actually this such abstract sum manifest in the observables we consider in the loop quantum gravity field. And that's why it's relevant. And what it shows here is that basically, despite the fact that I started with an operator, this operator that is the trace H, which depends only on the holonomy, and I was thinking only about this operator to construct the canonical structure. The canonical structure on its own somehow forces such abstract sum to take well, basically the structure of the state into consideration. All right, and then once you have this canonical structure, which is very much just the structure of the canonical structure of a harmonic oscillator, then the rest just follows just from quantum mechanics, no magic here. The whole work is basically done in this part, which is basically once you are given an operator, you have to make sure to derive a canonical structure which satisfies what is there in the red box. And that's in the case here of abelian gauge theory, it's a bit trivial. However, in the non-abelian case, it's not. And that's what I will be talking about in a moment. So as I was saying, okay, yeah. So what I was saying is that once you have your canonical structure, you just construct your coherent states that are the eigenvectors of your annihilation operators. If you have a tensor product, you do the tensor products of the coherent states. And basically, as you might expect, those will have some coherence properties. But the standard coherent properties with respect to annihilation and creation operators, that's trivial. But what you are interested in is the operator you started with, this observable. And then you can do some calculations. So for instance, here I abused a bit the notation. I wrote just H, but it's actually trace of H. And basically the expectation values, you can compute them and they give you something like that in this context. And they have this relative variance that depends on the modulus, and it has different limits. All right, so that's basically what an example of how this construction can be carried on. The simplest example you can think of with an abelian gauge theory and just this small closed loops that doesn't affect the other quantum numbers. A particularly interesting application of this is you are in a U1 gauge theory, so you are in Maxwell theory, and you have this Maxwell theory, and it's Hamiltonian. So here you have the electric field and the magnetic field. And once you do introduce this canonical structure, you can actually rewrite the whole Hamiltonian as in terms of those annihilation and creation operators, which is rather nice because basically what you are doing is that you are reformulating the dynamics as some sort of really dynamics on basically a space of finite number of harmonic oscillator, which might have its advantages. All right. So I'll go just quick to my example 2. So my example 2, I will take the non-abelian gauge theory, but think of it as a SU2. So I'm back again to having spins and intertwiners in my spin networks. There, the tau that is sitting there in the definition of the holonomy is just the generator of the algebra. So in SU2, it's something proportional to Pauli matrices in some representation, which I call there K. And then I will consider again just this simple graph excitation, the same one, just to make it simpler. And now one has to pay attention that at the vertices now there is an intertwiner space. So multiple mappings are possible. So graphically, I would say it would look like this way. So in the abelian case, as I showed you, you basically end up with a structure very much of a single harmonic oscillator, basically. because you have no intertwiner structure. Then you introduce your canonical structure that maps you between the number states. All right. In the non-abelian case, the picture looks more like this. And that means that actually you have multiple harmonic oscillators, but it's also they are not at the same level. Namely, that you can start with a graph. So the iota stands for the intertwiner. This label, this first label here, stands for the total number of loops, let's say in this example, that you have at the vertex. And the second label is what I'm about to explain now, which is think of those states as the ones that are corresponding because they have zero loops, no loops at all, no graph excitations. From the canonical perspective, that would be vacuum state. Because once you hit it with the annihilation operator, there is no loop. So it vanishes. So those are vacuum states. What happens in the more than differently than in the abelian case, that you go to the level, the intertwiner space, where there is already a loop. So when you add a loop, usually the dimension of the intertwiner space grows. It's never constant. So what happens is that now you have loop attached to your vertex, right? However, here, this zero here denotes that this state that you obtain came from a state, a vacuum state, which had zero loops. So there was no zero loops. When you go to next one, it's the same, but next one, actually you would end up with the fact that you have another vacuum state, except that this vacuum state, it does have already a loop. However, it gets annihilated nevertheless. And that's why the difference in the notation, which means that as an excitation by my operator, it has zero excitations. However, it still has one loop in its graph. But what does it mean? It means that basically whatever observable I considered in order to build this structure, this state cannot come, well, it doesn't have any antecedent. This cannot be obtained as an image of another state sitting on this space. And that's how the structure is organized, basically. So what you end up with is some sort of tower, but you have also an infinite number of vacuum states. And now for each of these vacuum states, you would have to consider there's some sort of canonical structure, and you make sure that everything satisfies those commutation relations properly. So basically, the higher you go in the tower of intertwiner space, the more vacuum states you will have available in your space. However, you always have those states that come from a previous vacuum. All right. And then basically you have to introduce some canonical structure. So you impose that you want to find operators that satisfy those commutation relations. So what does that mean is that when you go to this space where you have the zero denote that you have no loops at all, this space is annihilated by all annihilation operators. And then when you go higher in the tower with the intertwiner spaces, the annihilation operators will map each intertwiner space to the one below it, the one that has one loop less. And then, of course, this is not trivial. Now, this is not trivial in the sense that this is not something that, you can just impose and find. No, it's actually quite restrictive, and you have to construct or check that your operators are satisfying this.
Question?
Yes?
So in this U1 case, there was only one way of attaching this.
Yeah.
Because of the commutativity, it didn't matter whether we cut it and maybe retrace in a different order. At the end of the day, we can always order things in such a way that we have closed loop times whatever it was before. But in non-abelian case, we have to specify this definition more clearly. So what do you mean now by adding a loop?
So adding the loop is, so as I was saying,
you multiply again by by trace of holonomy, or you now install this loop in some different way?
Yes. So here I am very much talking more generally. So I'm not telling you exactly how this loop is attached to the vertex, Okay, from the geometrical point of view, if I'm thinking about the graph, then I can fix a prescription. Think, for instance, about some tangentiality conditions that I have at the vertex and so on. So geometrically, and I would like to do it in this way that actually they are all diffeomorphically equivalent, no matter how many loops I put. Okay, so I need this somehow this diff invariant prescription to implement these loops. However, this is not the only part. Once you fix, this is just basically the story of telling me exactly what you mean by graph change. You fix it exactly what it is. But there is the part which is about how everything couples at the vertex. And this is what I wanted to show here at the end of this slide, which is about the creations operators and the action of the canonical operators. Just one observation is that the creation operators that you need to have, and this is a condition on the observable you start with, they must be injective maps on the spaces. So this is already a condition from the start on which operators you are to consider. Now, once you have that, you can consider that your annihilation creation operator acts in this way. And what do? They actually are not only aware of the number of excitations, but they are aware of the vacuum they come from. This is how you would tackle this degeneracy in a way, or the presence of multiple vacuums. And they take that into account. This M here is basically this number of loops present in this vacuum state. And they take it into account in this coefficient when they are mapping the states between each other. And here it's actually still general up to this condition, of course, and well, the commutation that is sitting here. And I will show you just two examples maybe of operators where this works. Yes, here. So basically, as I was saying, there is no unique vacuum state in the non-abelian case. And there is no unique mapping between the intertwiners in the sense that if I want my canonical structure to exist, it's still not a strong condition to choose only one specific way of coupling that loop at the vertex. It's still not. And here there are two examples that actually we worked out, which is this, you can take, for instance, this operator as a start. And as you can see, it's a trace of H with the generator.
I have a remark to the organizers. So actually, for the first time, I'm attending this seminar via Zoom. Usually I'm there. And now I have to say that when I'm attending by Zoom, I don't see at all what you are showing with your.
Okay, so I'll try with the mouse.
With your wooden stick, I can see I can see you in some small square in the corner of my screen, but on the so either if you stop showing transparencies and just show view from.
Oh, no, I'll show you on the slide. So I'll show you on the Zoom with the mouse. So you can see the cursor moving, right? Pointer of the mouse.
Yes.
Hello?
Yes.
Yes, you can see it. Okay. So what I was mentioning is that, for instance, those are examples of operators you can start with in order to define a canonical structure. So one example that you can recognize because it manifests, for instance, in the definition of the Hamiltonian is this trace of H tau, right? And of course, it's not gauge invariant, this operator by itself. However, it's actually enough to define this canonical structure. And you can check actually accurately because the coupling here, because it's not gauge invariant, the coupling is rather a bit trivial in this sense because there are no fluxes that connect it and so on and so forth. Then actually those commutation relations are satisfied. So basically you can do something different, which is you consider just the trace of the holonomy as I showed in the abelian case. And it still works because again, the coupling here is also trivial. You can, if you look at it from the intertwiner perspective, in other words, it factorizes, okay? And as such, the commutation relations for the canonical structure would also be satisfied, okay? So you have to do it in a way case by case because now this canonical structure is not unique, but it's not arbitrary either. So some operators, some observables will be able to provide you such canonical structure, but others won't. Simply either, for instance, as I was saying, they will fail this injectivity condition, or the coupling for the intertwiners doesn't allow for this commutativity. One actually example here is what I show here at the bottom. But basically, so as I was saying, more generally, any set of commuting, closed and injective, and of course, densely defined operators, this OI, generating the same graph excitation can provide a canonical structure. And the way you would obtain it, as I was mentioning, is that you would introduce the tilde operator, which are basically normalization of this O operators that you have, and you use the O tilde to introduce the canonical structure. And then everything would work. One example that you make
actually writing holonomy dagger. You have this symbol here
yes.
several times. It's a little confusing because H alpha usually is considered for a given alpha. On the other hand, so H alpha dagger would be just complex conjugation of.
No, that's not that dagger.
Exactly, and you mean something.
No, it's not that dagger.
Because you mean changing alpha. So new holonomy.
No, this is
new
so.
alpha.
This is So this is the dagger in the sense.
This notation.
I know. Well, you have to use some notation. So it's either the dagger or the star, or you use the inverse. As you were saying, if I use the adjoint, it will be just the inverse. It's just the loop with the opposite orientation. Then
when you apply dagger to this operator A, then it is properly defined.
Yeah, the time ran out.
Okay, and then there will be a question time. Well, let us finish the talk, and then we're going to do this solve it.
All right. Yeah, so the only thing I want to mention here is that generically, as I was saying, you can do that. And one example that I give, actually, this is actually for you. It's this expression that manifests in the Hamiltonian, where you have the fluxes showing up here, and you have the sum. So actually, I cannot take this single operator here sitting inside the sum as an operator that would generate a canonical structure, because they do not commute. Okay, this set of operators do not commute, the ones that are sitting inside this. That's why you cannot take them. And what you can do is take the sum of all of them. Then you have actually in this set of operators, you have just one operator that would generate a set, basically one creation and one annihilation operator, one canonical structure that would basically have satisfy the needed properties. So that's basically how you would do it. And of course, the rest is basically once you have a canonical structure that is no different than before, it's just the canonical coherent state that would basically satisfy the coherence properties that are by construction meant to have. Okay, so to summarize, the goal here was to answer basically an open question that was present, that is, can one construct some coherent states for observables that actually change the graphs of the spin network states? And the answer is that you can, depending on what you consider, but in general, you can. The construction that I presented here admits various graph excitations, even non-local ones. In principle, there are no restrictions on the particular graph change. The question is, how do you implement it? In other words, how do you do the coupling in this case? And that comes with, of course, this freedom in the choice of the vacuum states and intertwiner mappings, because now you have intertwiner space that grow larger and larger, or at least they change the dimensions, so the number of vacuum states also changes, and the mapping can also vary, and then you adjust that according to actually the observable you would be interested in. As an outlook, I'd say that there is more to do, which is, for instance, exploring the dynamics of such states. If one considers dynamics or observables that are, such as actually the Hamiltonian itself, it's to explore how the evolution of such state would be. One can also, should explore other choices of the intertwiner mappings, which correspond basically to different choices of observables, or at least sometimes actually to just the way observables are, let's say, regularized. which would be, for instance, that if you take different volume operators, you would have different mapping correspondence. And finally is to explore actually more concretely different graphs. Here I gave you the example of the small closed loops, but in the literature, there are other graph excitations that are present, and one can actually extend the framework there. And it would be worth to investigate the semi-classical and continuum of such states. And that would be all. Thank you.
Thank you very much. So, and now, are there any questions? Perhaps first from here and then from people online. Okay. All right. So there is no question from the room. Do you have some more questions, please?
Yes, can I still have some question, even though I asked so many questions during the...
Sure.
So, if we look a bit more exactly at your construction, so you need, so actually you need some notion of diffeomorphism invariance of those states, right? Because you ignore difference in shape of loops. It doesn't matter what loop you add, it is just counted as more or less.
I mean, it matters in the sense of what I showed you here, namely that I wanted this simple canonical structure, which has this bosonic statistics, all right? But in principle, you can consider different statistics or actually make all, for instance, your loops distinguishable. But then when you make them all distinguishable, sometimes you can actually even make it ordered. And if you make them ordered, like somehow an ordered set, then even then you can still implement some sort of canonical structure. So in principle, I don't see any obstruction in changing the statistics, because that's basically what it is. When I make them distinguishable, undistinguishable, I'm making this choice of bosonic statistics. But nothing prevents me from making another choice. That was just the simplest one.
Yeah, but well, I think that this notion of freedom in choosing statistics, I would say it's a notion in freedom in constructing your example. But once you have a specific example, you cannot say, now I change statistics. You have to go home and prepare a new example. So in this case, we have the statistics is given by the construction, because we know that we know that when we multiply two holonomies, then there is no ambiguity. We mathematics tells us what is the difference in if you have different order. Okay, but so what I was saying is that they occupy some space and we ignore differences between different, for instance, shapes of loops. So it means that we average with respect to diffeomorphism. So there is, so probably you are choosing this Hilbert space, which I call vertex Hilbert space.
In this case, for this particular graph change, yes, that would be the choice.
Yeah, but that would be
too much in those technicalities. That's why.
Yes, of course. You couldn't explain it all, but just if we want to be a little more explicit, yeah. Okay, thank you.
Yeah, that's correct. Yes. It's definitely the case. That's basically what happens. Let's say the motivation for those particular examples is those works on the dynamics and those Hamiltonians that we considered, especially when we are working in the vertex Hilbert space. That's that was basically the first motivation for it. But then it turns out that actually there is more.
And here you simplified all the problem also for the sake of clarity of presentation by choosing planar graphs or somehow referring to our intuition about planar graphs. But if they are not planar, then there are more ways of attaching a loop, and we have to.
There are, yes. Yeah. But if we consider, for instance, the prescription for those special loops that we consider in the dynamics, then that would work. In the vertex Hilbert space, it would work. So that prescription actually is sufficient for this.
Yeah, I just can see a lot of
Yeah.
lot of subtleties which you also have to take care of. And
That's correct.
and now you are saying that if we consider the scalar constraint operator in some simple form, then it can be written in some consistent way by using those A operators.
That's correct. Yes.
I see. Very, very good. Okay, so I can see how, if you have well-defined A operators, how you can define coherent states. And now the question is, what is the action of this constraint operator on those coherent states? Are they somehow preserved, or is there?
That's one of the points to explore. That's what one of the points I put in the outlook. So I know I can obtain this structure which is as close to as possible to the mapping structure of the Hamiltonian constraints, but one has still to check how it behaves under evolution. So that is something I didn't check yet.
Okay, so thank you.
Okay, thank you very much. And I think this closes the discussion. So let us thank the speaker again.
Thank you.